Hi everyone, welcome to goclasses. In this lecture, we will study SDD, syntax directed definitions. Remember, in the semantic analysis, we have already seen this SDT in the part 1, and this is part 2. In this part 2, we will study SDD. Okay, so syntax directed translation scheme, or I can say translation scheme, this we have already studied with all the gate PYQs in the previous lecture. In this lecture, we will study SDD with all the gate PYQs. Okay. So our topic is syntax directed definitions SDD. Now let's do some recap of the previous lecture. In the previous lecture, we have seen what is the meaning of semantic analysis, what semantic analysis means. Now, how does the compiler design do semantic analysis? The compiler, how it will do the semantic analysis? We have already seen that to perform lexical analysis, we use regular expression. Remember the lexical analyzer, or I can say the scanner. The scanner, for the purpose of lexical analysis, it will use a formal tool, a formal mechanism, or a formal specification, that is regular expression. Similarly, the syntax analyzer, or I can say the parser, for the purpose of syntax analysis, we will use a formal mechanism or formal specification or a tool, that is context free grammar. Similarly, the semantic analyzer, for the purpose of semantic analysis, to do the semantic analysis, we use a tool, or I can say a formal specification or a mechanism, that is SDD or SDT. These are different. In the previous lecture, already this SDT, syntax directed translation scheme, we have already studied. In this lecture, we will study syntax directed definition. Okay, let's quickly do the recap of SDT. So, recap of SDT, or I can say recap of previous lecture. So, the concept of SDT means syntax directed translation scheme. In short, you can call it translation scheme, or you can call it SDTS, or you can call it SDT. So, the concept of the definition of SDTS we have already seen. What is this SDTS? The definition is very simple. A syntax directed translation scheme. This is a context free grammar with program fragments embedded within production bodies. Remember, whenever you have a production, if you have a production A going to XY, now here remember, this complete thing is called production. And this A, this is called head of the production. And this XY, this is called body of the production. Okay. So I can say in this production, the LHS is called head of the production, and this RHS is called body of the production. Okay, I hope you understood. So you can see the syntax directed translation scheme, SDT. What is this? This is a context free grammar with program fragments embedded within production bodies. These program fragments, these are called semantic actions, and they can appear at any position within the production body. Okay, production body means the right side of the production. Okay, this left side of the production, this is called head, and you can see this right side of the production, this is called body. So in this body, in this production body, these program fragments, which are called semantic actions, they can appear at any position. So you can see the semantic actions, or I can say the program fragments, they can appear at any position within the production body. Very simple. I hope you understood. So you can see a context free grammar with program fragments embedded within production bodies, that is called SDTS, syntax directed translation scheme. I hope you understood. Okay. Already in the previous lecture, this SDTS we have studied, and also each and every gate PYQ already we have solved. So you are already a master of SDTS. Okay. So one more thing, you already know that in this SDTS, in short, you can call it translation scheme. This translation scheme, this describes the order and timing of attribute computation. Remember, with the grammar symbols, we associate attributes, that we already know. In the previous lecture, we have seen that attributes are associated with grammar symbols. And this translation scheme, or I can say this SDTS, syntax directed translation scheme, it explicitly describes the order in which these semantic actions will be performed. Basically, the translation scheme, it explicitly describes the order in which the attributes will be computed. Okay, for example, if you have this SDTS, let's assume this is the translation scheme, and let's assume that here you have some semantic action S1, some semantic action S2, some semantic action S3. Now remember, translation scheme describes explicitly the order in which semantic actions will be executed, the order in which attributes will be computed. So here you can see in this translation scheme, you can see that before we see X, we will perform this semantic action S1. Okay, so you can see in which order these semantic actions will be executed. So you can see this semantic action S1 will be executed before we see any symbol derivable by X. Basically, before we see X, this semantic action will be executed. You can see after we see X and before we see Y, the semantic action S2 will be executed. And after we have seen X comma Y both, then the semantic action S3 will be evaluated, or I can say executed. Very simple. Okay. So this is the idea. Now we will study SDD, syntax directed definition. In the previous lecture, syntax directed translation we have seen. All the gate PYQs based on SDT, or I can say based on SDTS, we have already completed. Okay. In this lecture, we will study SDD, syntax directed definition. So let me tell you what are the topics that we will study in this lecture. So in this SDD, these are the topics that we need to study. One by one, we will study all these topics, all these definitions, or I can say all these concepts. So you can see, first we will see the concept of attributes. Then we will see SDD definition. Then we will see difference between SDD and SDT. Okay. Then we will see attribute grammar definition. Then we will see the definition of synthesized and inherited attributes. A lot of practice we will do. Gate PYQs we will solve. Then we will see S attributed SDD and L attributed SDD. Here also all the gate PYQs, all the gate questions we will solve. A lot of practice we will do. Then we will see evaluation of SDD. How we can evaluate SDD. So to evaluate SDD, we use a concept of dependency graph. So that also we will see here. Then we will see what is circular SDD and also all the gate PYQs based on SDD, syntax directed definition. Okay. So in this sequence, these topics, these concepts we will study. So let's study the first concept in SDD, that is attributes of grammar symbols. So in the previous lecture also I told you this point that we associate attributes with non-terminals and terminals. Here we will see this concept of attributes in more detailed way, I can say in a more comprehensive way. So attributes of grammar symbols, basically in SDD, also in SDT. Okay, what we do, we associate attributes with grammar symbols. When I say grammar symbols, it means non-terminals or terminals. So we associate attributes with non-terminals and terminals. Now you might be thinking, which attributes we will associate with terminals and non-terminals? So let me tell you, the attributes that we associate, they will depend on the kind of semantic analysis that we want to perform. Okay, so you can see the attributes are chosen based on the semantic information, the semantic analysis, or I can say the semantic information that we want to compute. So remember, the context-free grammar, the CFG, so that will define the syntax, or I can say syntax will define the structure, and attributes will define the meaning. So you have the context-free grammar. In that context-free grammar, with the grammar symbols, with the non-terminals, with the terminals, we associate attributes. These attributes will define the meaning. Okay, remember, semantic analysis means what? Semantic analysis means the analysis of meaning. Yes or no? We want to make sure that our program is meaningful. Our source program is meaningful. This is what we want to ensure in the semantic analysis. And you can see in this semantic analysis, we attach the meaning with the context-free grammar. This I told you in the previous lecture also. With example, I told you this point that to perform the semantic analysis, what we do? we use context-free grammar, and with that context-free grammar, with the productions of context-free grammar, we attach the meaning. And when I say we attach the meaning, what it means? It means we attach the semantic actions. Also, we attach attributes with the grammar symbols. Okay, so let's keep it simple. Basically, we associate attributes with the grammar symbols. We associate attributes with the non-terminals and terminals. And the attributes are chosen based on what kind of semantic analysis we want to perform. Do we want to perform type checking? If we want to perform type checking, then the attribute that we associate, that will be type attribute. Okay, with every non-terminal we can associate type attribute. So if we want to calculate value, if we want to evaluate some expression, we want to compute the value of some expression, then we can associate the attribute val. Okay, that attribute we can associate with the grammar symbols. So basically, what kind of semantic analysis you want to perform, depending on that attributes are chosen, depending on that attributes are associated with the grammar symbols. Okay, and these attributes, they will basically define the meaning. Along with the semantic actions, attributes will define the meaning. Okay, very simple. Now let's see some example. Let's consider this example. Let's assume our semantic goal. You can see the semantic analysis that I want to perform, or I can say our semantic goal, let's assume that is expression value evaluation. We want to evaluate expression. So in this case, which attribute I will choose for the grammar symbols? Which attribute I will choose? Very simple. This val, yes or no? This value attribute, or I can say val, this attribute I can choose. This attribute I can associate with the grammar symbols. Okay, so you can see we associate attributes with non-terminals and terminals. One more thing, let me tell you. This we will see in more detailed way also. But the point is, attributes for terminals have lexical values that are supplied by the lexical analyzer. Remember, the attributes for the non-terminals, when we associate attributes with the non-terminals, then these attributes for the non-terminals, these attributes will be computed by the semantic actions, these semantic rules. Okay, but remember, the attributes that we associate with the terminals, these will be computed, or I can say these values, the values of these attributes, the values of attributes of terminals, these values will be supplied by the lexical analyzer. We cannot write a semantic rule, we cannot write a rule to compute it. Okay, very simple point. I am saying that we associate attributes with non-terminals and terminals. When we associate attributes with non-terminals, when we associate attributes, then these attribute values will be calculated using the rules, using these semantic rules. Okay, but when we associate attributes with the terminals, then the values of these attributes which are associated with terminals, the values of these attributes will be supplied by the lexical analyzer. We cannot compute it, we cannot write a semantic rule to compute it. We cannot compute it. The attribute values for non-terminals will be supplied by the, sorry, the attribute values for the terminals, the attribute values for the terminals will be supplied by the lexical analyzer. I hope you understood this. Okay, so let's see, if our semantic goal is expression value evaluation, then what we will do, we will choose this val, this attribute we will choose for our grammar symbols. So you can see that corresponding to this production, which semantic rule we will write? Our purpose is expression value evaluation. We want to evaluate the expression value. Okay, so you can see corresponding to this production, first of all, with this non-terminal t, I will associate attribute val. Okay, and similarly with this terminal num, with this terminal, I will associate this attribute val. I told you that the attribute values for terminals, these attribute values for terminals, these will be supplied by the lexical analyzer. So this num.val, this will be supplied by the lexical analyzer. I cannot compute it, I cannot write a semantic rule to compute it. But you can see the attribute values for non-terminals, to calculate them I can write semantic rule. Okay, so you can see corresponding to this production, In this production, T is going to num. This is a terminal. Okay. And with this terminal also, this val, this attribute is associated. And you can see this num dot val, it will be supplied by the lexical analyzer. So finally this T is going to num. So this T dot val, that also will be same as num dot val. Okay, so this is the semantic rule. Using this semantic rule, we are computing T dot val, means this val attribute of non-terminal T. Very simple. Now you can see corresponding to this production, look at this production, E going to E1 plus T. Remember here this E1, this is same as this E, both are basically same. But to differentiate which E I am talking about, I am using this subscript. Okay, so basically remember this E comma E1, they are basically representing the same variable. They are the same variable, but I can say they are different instances of the same variable. Okay, these are different instances of the same variable. Okay, so you can see corresponding to this production, E going to E1 plus T. So what will be E dot value? E dot value, that will be equal to E1 dot value plus T dot value. Okay, very simple. I hope you understood. So you can see that which attributes are associated with terminals and non-terminals, that depends on what type of semantic analysis I want to perform. I hope you understood. Let's see another example. Let's assume that our semantic goal is type checking. I told you that one of the one of the very important tasks of semantic analyzer, that is type checking. Yes or no? In the semantic analysis, one of the most important thing to do, one of the most important tasks to do, that is type checking. Type checking means we want to ensure that operands have the same type, or I can say operands are of compatible types. Okay, so you can see that let's assume that our semantic goal, that is type checking. In this situation, what we can do, with the grammar symbols we can attach this type attribute. Okay, this type attribute we can attach, we can associate this type attribute with the grammar symbols. So you can see, for example, corresponding to this production, here you have T going to ID. So you can see T dot type, that will be same as ID dot type. Okay, T going to ID. So whatever is ID dot type, that will become T dot type. Okay, so you can see corresponding to this production, here what can you say about E dot type? So you can notice, if even dot type and T dot type, if they are same, then E dot type, that will become even dot type. But remember, if even dot type and T dot type are different, then in that case you can give error. Okay, because type mismatch. Yes or no? If there is a type mismatch, then you can give error. So you can see corresponding to this production rule, here we have this production rule, E going to E1 plus T. So you can see, if E1 dot type and T dot type, you can read this, if E1 dot type and T dot type, if they are same, then E dot type will become E1 dot type, else error. Else error means type mismatch. Okay, I hope you understood. So overall, this is what we have seen, that we associate attributes with grammar symbols. When I say grammar symbols, it means terminals or non-terminals. So we associate attributes with non-terminals and terminals. And remember, attributes associated with grammar symbols depend on the kind of semantic analysis that we want to perform. The attributes are chosen based on what semantic information we want to compute. And these attributes, they basically define the meaning. Okay, I hope you understood. So the concept of attribute of grammar symbols, I hope you understood. Okay, one more thing I told you, that for the terminals, the attribute values will be supplied by the lexical analyzer. For the terminals, the attribute values cannot be calculated using semantic rules. We cannot write semantic rules to calculate the attribute values for terminals. For the terminals, the attribute values will be supplied by the lexical analyzer. Okay, very simple. So you can see, we associate attributes with non-terminals and terminals. Then what we do? Then we attach semantic rules to the productions of the grammar. These semantic rules will describe how the attributes will be computed. Basically, in this SDD, let me tell you, in this syntax directed definition, in this SDD, basically, we have context free grammar plus attributes plus how to compute these attributes. For that we have semantic rules. Okay, in simple words I can say this is what SDD means. Okay, so remember SDD, syntax directed definition, it simply means context free grammar, CFG, plus attributes associated with grammar symbols, attributes associated with non terminals and terminals, plus how to compute, how to calculate these attributes. For that we have semantic rules. These semantic rules we write corresponding to the productions. So you can see context free grammar plus attributes plus semantic rules. These semantic rules will be used to compute the attributes. Okay, this thing is basically called SDD, syntax directed definition. Okay, so that is what I'm writing here. You can see we associate attributes with the non terminals and terminals. Then we attach semantic rules to the productions of the grammar. These semantic rules will describe how the attributes will be computed. And one more thing, let me tell you, if you have non-terminal x or any grammar symbol, it can be terminal, it can be non-terminal. If you have a grammar symbol x, and if you want to indicate the attribute a of x, then you can write x dot a. So remember, x is grammar symbol, it can be terminal, it can be non-terminal, and this x has attribute a. For example, let's assume x has attribute int. Okay, or I can say x has attribute, let's assume this val. Then you can see to indicate this attribute val of x, you can write x dot val. This x dot val, it indicates the attribute val of x. Okay, so you can see if x is a grammar symbol and a is one of its attributes. Remember, a grammar symbol can have many attributes. Okay, you can have multiple attributes associated with a grammar symbol. So you can see a grammar symbol can have multiple attributes associated, or I can say a grammar symbol can have a finite set of attributes associated with it. So you can see if x is a grammar symbol and a is one of its attributes, then you can write x dot a to denote the attribute a of x. Okay, and also this important thing I told you, that attributes for terminals have lexical values which are supplied by the lexical analyzer. There are no semantic rules in SDD itself for computing the values of attribute for terminal. So for terminals, the attribute values will be supplied by the lexical analyzer. For terminals, the attribute values cannot be computed using semantic rules. Okay, very simple. So I hope you understood. We have seen the concept of attributes of grammar symbol. The next topic, the next concept that we need to study, that is syntax directed definition. The definition of syntax directed definition. So let's see. So what is the definition of SDD, syntax directed definition? So you can see SDD, or I can say syntax directed definition. This is basically a context free grammar in which attributes are associated with grammar symbols, means attributes are associated with terminals and non terminals, and semantic rules are associated with productions to compute these attributes. Okay, very simple. So you can see a syntax directed definition SDD consists of three things. There are three things in SDD. One is context free grammar. The next is a set of attributes, a finite set of attributes associated with grammar symbols, means a finite set of attributes associated with terminals and non terminals. And we have semantic rules that will define how these attributes will be computed. Okay, so you can see semantic rules associated with productions to compute these attributes. Very simple. So SDD, this means context free grammar plus attributes plus semantic rules to compute these attributes. Okay, so you can see this example. This is a SDD. Okay, this overall this structure, this is SDD, syntax directed definition. So here you can see we have grammar. This is the context free grammar. Okay, so these are the productions. This is the context free grammar, and you can see that with the grammar symbols, with the non terminals, these are the non terminals, and you can see this is a terminal. So you can see with the grammar symbols we have associated attributes. So you can see this attribute VAL. Okay, this attribute VAL, this attribute we have associated with the non-terminals and terminals. Okay, so you can see grammar plus attributes associated with grammar symbols plus, you can see these are the semantic rules which are used to calculate, to compute these attribute values. Okay, with the grammar symbols we are associating finite set of attributes. Now to calculate these attributes, to calculate the values of these attributes, we associate semantic rules with the productions. Okay, you can see here that with this production this semantic rule is associated, with this production this semantic rule is associated, with this production this semantic rule is associated, like that. Okay, I hope you understood. So overall this structure is syntax directed definition, SDD. Now you might be thinking that similar definition we have seen for SDT, correct? In the previous lecture, when we were discussing syntax directed translation scheme, SDT, then similar definition we have seen. In SDT also we have context free grammar plus attributes associated with the grammar symbols plus semantic actions. Yes or no? So you can see the similar definition we have seen for SDT and similar definition we have seen for SDD. Then what is the difference between these two? You might be thinking. Okay, so let's see the difference first. Then we will come back to SDD, because many of you might be thinking what is the difference between SDD and SDT. Okay, so let's see the difference. So you can see a small detour. Let's see the difference between SDD and SDTS, means syntax directed definition versus syntax directed translation scheme. In the previous lecture also I told you this difference actually. The difference is very simple. Remember, SDD, it will tell you what to do, but it will not tell you how and when to do. And remember, this SDTS, it will tell you what to do, how to do, when to do, everything. So remember, SDD, this is declarative. It will declare what to do. And SDTS, this is procedural. It will tell you the procedure about how to do. Okay, how to perform a task. I hope you understood. So remember, SDD, this is basically good for defining. If you want to define what task to do, you want to carry out some semantic task. Okay, so remember, whichever semantic task, whichever semantic analysis you want to carry out, to define that, you can write SDD. Okay, so I can say this SDD, this is easy if we are defining a semantic task. Okay, if we are defining the semantic analysis that we want to perform, if we want to define it, then this SDD is good way. But remember, if we want to implement, if we want to evaluate, then SDTS is good, because SDTS will tell you what to do, how to do, when to do, everything. Okay, so let's see the difference here. You can see the difference between SDD and SDTS. SDD, syntax directed definition, it will specify what to do, means it is declarative. It will declare what to do, means which semantic task to do, which semantic analysis to perform. So that will be specified by SDD. SDD will specify what to do. And you can see SDTS, it will specify what and when to do, means it is procedural. So you can see SDD, it does not specify the evaluation order. The evaluation order is not specified by SDD. But you can see that this evaluation order, or I can say execution order, is explicitly specified by SDTS. So you can see SDD will specify what semantic computation is to be done. You can see this syntax directed definition, it will specify what semantic computation is to be done. And this SDTS, it will specify what and when the actions will execute, means the execution order, the evaluation order is explicitly specified in the SDTS. I hope you understood. So you can see in the previous lecture when we were discussing SDTS, we have already seen that the position of semantic action in a production body will determine the order in which the semantic action will be executed. Okay, the order in which the semantic actions will be executed, the order in which attributes will be calculated, that order is explicitly specified in the SDTS. Okay, and you can see the position of a semantic action in the production body will determine the order in which the action will be executed. Okay, I hope you understood. So the difference between SDD and SDTS, I hope you understood that SDD, this is declarative. It will specify what to do, which semantic analysis to perform, which semantic computation to perform, that will be specified by SDD. And you can see SDTS, this will specify what semantic action to perform, or I can say what semantic computation to do and when to do. Okay, means the evaluation order is explicitly specified in the SDTS. I hope it is clear. Okay, so you can see, let's see one more difference. The first difference we have seen, that is SDD will specify what to do. SDTS, it will specify what and when to do. This is first difference that we have seen. Now let's see the second difference. Understand the second difference also. The second difference is in SDTS, in syntax directed translation scheme, in SDTS, the semantic rules are embedded within the production bodies and they can appear at any position in the production body. Yes or no? In SDTS, the semantic actions, or I can say the program fragments or the semantic rules, they are embedded within the production bodies. Means they can appear, the semantic rules, the semantic actions, they can appear at any position in the production body. But remember, in SDD, the semantic rules are written separately from the grammar. Means the grammar productions are separate and you can see the semantic rules are separate, like that. And in this SDTS, the grammar productions and the semantic actions, they are mixed in each other. Okay, like that. I hope it is clear. So you can see the difference here. Look at look at this SDTS. This is a syntax directed translation scheme. Here you can notice that, look at this production. So in this production, you can see here the semantic action is placed. Okay, similarly you can see here, look at this production, r going to plus tr, and you can see this semantic action is placed after plus t and before r. So I can say in the middle of production body, this semantic action we have placed. Okay, but notice one thing, in the SDD, in the syntax directed definition, the grammar productions are separate, semantic rules are separate. Okay, this separation we have, the grammar productions are separately written and the semantic rules are separately written. I hope you understood this point. Remember, corresponding to every production, we are writing a set of semantic rules. Okay, with this production, this is the semantic rule. Corresponding to this production, this is the semantic rule. But the point is that these are the productions written separately, and these are the semantic rules written separately. This is what we do in the SDD. But you can see in this SDTS, you can see the semantic rules, or I can say the semantic actions, they can be placed at any position in the production body. Okay, so these are the differences. I hope you understood. So you can see this is what I have written here, that in SDTS, the semantic rules are embedded inside production bodies. The semantic rules can be placed, the semantic rules can appear at any position within the production body. But in SDD, the semantic rules are written separately from grammar productions. Okay, so you can see this is the second difference and this is the first difference. I hope you understood the difference between SDD and SDTS. Okay, one more thing, let me tell you that for definition purpose, for defining purpose, this SDD is good, and for evaluation purpose, for execution purpose, for the implementation purpose, SDTS is good. Okay, so both have their advantage and disadvantage, but I hope you understood the difference between SDD and SDTS. Okay, so you can easily see in the SDTS, the semantic actions can be placed at any position in the production body. Okay, you can see this here, that in this syntax directed translation scheme, the syntax directed translation scheme, this is a context free grammar with program fragments which are called semantic actions, and these semantic actions are embedded within production bodies And these semantic actions can appear at any position within a production body. At any position within a production body, these semantic actions can appear. Okay, very simple. You can see here this point also, that in the translation scheme, means in SDTS, in syntax directed translation scheme, the order and timing of attribute computation, that is explicitly specified. Okay, means in which order the attributes will be computed, in which order the semantic actions will be evaluated, the semantic actions will be performed. Everything is explicitly described in the SDTS. Okay, very simple. So you can see this. All these things related to SDTS, syntax directed translation scheme, all these concepts we have already seen in the previous lecture. This is just a quick recap, okay, to explain the difference between SDD and SDTS. Okay, so you can see, if you have this production B going to XY, actually the production is B going to XY. This is the production. But you can see in this SDTS, the semantic actions, they can appear at any position in the production body. So you can see here this semantic action we have put. Okay, this is the semantic action A. So you can see when this semantic action will be executed, when this semantic action will be performed. So you can see that after you have seen X, before you have seen Y, the semantic action A will be performed. Okay, so you can see an action may be placed at any position within the production body. It is performed immediately after all the symbols to its left are processed. For example, if you have a production B going to X, semantic action A, Y, then this semantic action A is done after we have recognized X. Okay, very simple. After we have recognized X, this semantic action A will be performed. Okay, very simple. So I hope you understood that in the SDTS, in the translation scheme, in the SDT, you can see the semantic rules, the semantic actions, they can appear at any position in the production body. But you can see in this SDD, in this syntax directed definition, we have grammar production separate, semantic rules separate. Okay, like that. Very simple. And I told you this point that this syntax directed definition, this is good for high level specification. Like as a human being, if I tell you to perform some semantic analysis, and to carry out that semantic analysis, you are writing SDT or SDD. Okay, you are writing SDT or SDD, you are writing to carry out that semantic analysis. Then remember, for you, this SDD will be better. Okay, so you can see this SDD, syntax directed definition. This is high level specification, hiding the implementation details. Okay, and you can see translation scheme, or I can say SDTS, syntax directed translation scheme. So this SDT, this is more implementation oriented, means it will indicate the order in which semantic rules are evaluated, the order in which semantic rules, the order in which semantic actions will be performed, the order in which semantic rules will be evaluated, that order is indicated in this translation scheme. Okay, so you can see between both the notations, these are the notations. Either you can use SDD for semantic analysis, or you can use SDTS for semantic analysis. Okay, but remember, between these two notations, this SDD, this is more readable. Okay, that is the reason it is more useful for specification. And this translation scheme, this is more efficient for implementation, or I can say for execution. So you can see that it is more useful for implementation. So you can see that this SDTS, you can think of this SDTS as a implementation of SDD. Okay, so this SDD, I can say this syntax directed definition, this is more useful for specification, to specify what to do. Okay, to specify the semantic analysis that we need to perform, to specify that, this SDD is more helpful. But you can see for implementation, for evaluation, for execution, this SDTS, this translation scheme will be more useful. Okay, I hope you understood. So we have seen the difference between SDD versus SDT. Okay, I hope you understood. So this difference again we have seen in the previous lecture, also we have seen, again we have seen. Okay, all about SDT we have already seen in the previous lecture with all the get PYQs. Now let's come back to SDD. Okay, we were discussing SDD. In this SDD, we have already seen the concept of attributes. Attributes are associated with terminals and non-terminals. And for terminals, the attribute values are supplied by the lexical analyzer. And for non-terminals, the attribute values are computed using semantic rules. Semantic rules are associated with grammar productions. Okay, also I told you in this SDD, the productions are written separately and the corresponding semantic rules are written separately. We don't mix them. Okay, in SDT what happens? The semantic rules are embedded within the production bodies. But you can see in this SDD, the productions are separate and the corresponding semantic rules are separately written like that. Okay, very simple. And the semantic rules, they are associated with the productions, like this is the production, this is a corresponding semantic rule. So you can see semantic rules are associated with productions, and these semantic rules are used to compute the attribute values. Okay, and for terminals the attribute values are supplied by the lexical analyzer. For terminals the attribute values are not computed using semantic rules. Okay, very simple. So far this is what we have seen. Now let's come back to SDD, syntax directed definition. So the definition we have already seen that SDD. What is SDD? It is a context free grammar. You can see SDD, it is a context free grammar with attributes associated with grammar symbols and semantic rules associated with productions to compute these attributes. Okay, very simple. This is the example of SDD. You can see productions are written separately and the corresponding semantic rules are written separately. Okay, very simple. Here you can notice that in this SDD, you can notice that with all the grammar symbols, we are associating this attribute VAL. Okay, you can see with all the grammar symbols, this attribute VAL, this attribute is associated. And you can see that with the productions, the semantic rules are associated, and these semantic rules are used to compute the attribute values. Okay, you can see for example here this e dot val, the val attribute of e, that will be calculated using this semantic rule, and this semantic rule is saying that e dot val, this is same as v t dot val. Okay, means whatever is t dot val, that same value will become e dot val. Okay, so like that, I hope you understood. You can see corresponding to this production, in this production we have t going to t1 star f. Remember this t comma t1, this subscript 1, what this indicates? It indicates the different instances of same variable. Remember t comma t1, they are the same variable, they are the same non-terminal, but to differentiate which t I am talking about, we are using this subscript, or I can say that this t comma t1, these are different instances of the same variable. Okay, so you can see corresponding to this production, t going to t1 star f, what will be the semantic rule corresponding to this production? That will be t dot val, that will be equal to t1 dot val multiplied by f dot val. Okay, so like that. So basically this is a SDD for calculator. Okay, simple calculator which can do plus and multiplication, which can do addition comma multiplication. So this is a SDD for calculator to calculate the value of expression. Okay, very simple. You can consider this SDD. Here we have another SDD. You can see these are the productions and these are the semantic rules. And here you can notice one thing, you notice with the non-terminal B, what are the attributes associated? On one side, I am writing the grammar symbols, and you tell me the attributes associated with the grammar symbols. Attributes associated. Tell me with the grammar symbols, what are the attributes that are associated? So you can see we have grammar symbol B, which is a non-terminal. With this grammar symbol B, which are the attributes associated? So you can see POS, yes or no? Okay, so I can say POS. Is there any other attribute associated with non-terminal B? So you can see that is VAL. Yes or no? VAL. Okay, so you can see. Remember, B comma B1, they are the same variable, different instances of same variable. B comma B1, they are the same variable. So you can see that POS, VAL, POS, VAL. Okay, you can just see here. We only have POS comma VAL. Okay, that's it. And you can see, what about D? Non-terminal D. Which attributes are associated with non-terminal D? Tell me. So you can see that is POW. Okay, and you can see VAL. Is there anything else? POW, VAL, POW, VAL. That's it. Okay, POW comma VAL. Okay, yes or no? So I hope you understood this point. So notice one thing. One thing you notice here, that you can see this POW attribute is not associated with non-terminal B, and this POS attribute is not associated with non-terminal D. Is this clear? So remember, with every non-terminal, or I can say with every grammar symbol, a finite set of attributes are associated. But remember, different grammar symbols can have different set of attributes associated. Is this point clear? It's not necessary that all the grammar symbols will have same set of attributes associated. For example, you can see this POS, this attribute is not associated with non-terminal D. This POW, this attribute is not associated with non-terminal B. Okay, I hope you understood this point. So with every grammar symbol, a set of attributes is associated, and with different grammar symbols, this set of attributes can be different. Okay, very simple point. So this is the overall conclusion. So far what we have seen the definition of SDD, syntax directed definition. So you can see a syntax directed definition is a context free grammar together with attributes and rules. Okay, this we have already seen. What is syntax directed definition, SDD? This is a context free grammar together with attributes and rules. Okay, attributes are associated with grammar symbols and rules are associated with productions. Rules mean semantic rules. These semantic rules are associated with productions and attributes are associated with grammar symbols. You can see we associate attributes with non-terminals and terminals. Then we attach rules, semantic rules, with the productions of the grammar, and these rules will describe how the attributes are computed. So you can see a syntax directed definition. It associates with each grammar symbol a set of attributes. Okay, in this syntax directed definition in SDD, with each grammar symbol, a set of attributes are associated, and you can see with each production, a set of semantic rules are associated, and these semantic rules, they will compute the values of attributes associated with the symbols appearing in that production. Okay, notice here one more thing. You notice that corresponding to this production, look at this production. Corresponding to this production, can you see multiple semantic rules are associated? Yes or no? With this production, multiple semantic rules are associated. Similarly, with this production, multiple semantic rules are associated. Okay, is this clear? This is what I'm saying here. You can see that with each production, a set of semantic rules are associated for computing the values of attributes associated with the symbols appearing in that production. Okay, simple. I hope you understood. The next definition, that is attribute grammar. This is just a simple definition. So let's see this. What is the definition of attribute grammar? Attribute grammar is basically a SDD without side effects. Okay, this is the simple definition. What is attribute grammar? It is a SDD, means it is a syntax directed definition. SDD without side effects. SDD without side effects. This is called attribute grammar. Now you might be thinking, what is the meaning of side effect? What this side effect means? Okay, so let me tell you. The definition of side effect is very simple. From the SDD point of view, syntax directed definition, from SDD, or I can say from the attribute grammar point of view, what is a side effect? The name itself is telling you side effect. Side effect simply means if you change anything other than the attribute values, means if you compute or if you do any changes outside the attribute values, if you compute or if you do anything other than computing the attribute values, then that is called side effect. Is this point clear? Let me give you some examples. For example, if you are printing the output on the screen, then basically printing, when you print the output on the screen, that is a side effect because you are doing something which is different from attribute computation. If you do anything other than attribute computation, if your semantic rule does anything other than attribute computation, then that is called side effect. Is this clear? So some examples I have written here, you can see some examples of side effect. For example, when you print output on the screen or when you print the result on the screen, so when you are printing the output on the screen, then basically you are doing something other than attribute computation. Yes or no? So you can see printing on screen, or I can say printing the output, that is a side effect. Another, for example, when you modify the symbol table, if you insert the type information in the symbol table, I told you that semantic analyzer will insert the type information in the symbol table. Yes or no? In the previous lecture, we have seen this, that the semantic analyzer, it will insert the type information in the symbol table. So that is also side effect. Yes or no? You are doing something other than attribute computation, then that is side effect. That's it. Very simple. This is the simplest definition. So you can see printing output on the screen, that is a side effect. Entering the type of an identifier into the symbol table, that is a side effect. Modifying a symbol table, that is a side effect. Changing any external data structure, that is a side effect. Anything you do other than attribute computation, that is a side effect. So if your semantic rules, the semantic rules in your SDD, if they only compute the attribute values, then it will be called attribute grammar. The name itself is telling you attribute grammar. Attribute grammar means this is a SDD in which the semantic rules will compute only the attribute values. That's it. Nothing else will be done. Nothing other than attribute computation will be done by the semantic rules. Okay, this type of SDD is called attribute grammar. Did you understand the definition? Let me know. A question came in the GATE exam based on the definition of attribute grammar. Basically, based on this screenshot, what you have in front of you right now, based on this, one question has come in the GATE exam which was asking the definition of attribute grammar. So I hope you understood the definition of attribute grammar. Attribute grammar is basically an SDD without side effects is called attribute grammar. Now let's see the definition of side effect. What is the meaning of side effect? So in the context of SDD, or I can say in the context of attribute grammar, a side effect is any semantic action. A side effect is any semantic rule that changes something outside the attribute values of the grammar symbols. Means if you do anything other than computing the attribute values of the grammar symbols, then that will be called side effect. And these are the examples. These are some of the examples of side effects. So you can see if you have a SDD, if you have a SDD in which all the semantic rules compute the attribute values of the grammar symbols, then such SDD will be called attribute grammar. The name itself is telling you attribute grammar means in this attribute grammar, or I can say in this SDD, all the semantic rules will compute the attribute values of the grammar symbols. That's it. Okay, I hope you understood. Consider this example of side effect. You can see we have this production, and corresponding to this production, this semantic rule I have written. You can see this is the production L going to E. Corresponding to this production, this semantic rule I have written, that is print E dot val. We are printing E dot val. So you can see when I print E dot val, am I computing E dot val? Am I computing the attribute value? Tell me. No, I am not computing the attribute value. I'm printing e.val on the screen. Yes or no? So this is a side effect. Okay. And if you have this type of semantic rule in your SDD, then it is not an attribute grammar. Okay. So you can see here an SDD without side effect means no displaying on the screen, no modifying the symbol table, etc. Okay. So you can see an SDD without side effect is called attribute grammar. In short, you can call it AG. Okay. Very simple. So why it is called attribute grammar that we have seen, you can see that an SDD without side effect is called attribute grammar because all the semantic rules, they will basically compute the attribute values of grammar symbols. That's it. So you can see all the semantics are expressed solely through attributes and their dependencies. Okay, means we are computing the attribute values from other attribute values. Okay, so you can see this type of SDD is called attribute grammar. I hope you understood. So you can read this that an SDD without side effects is called attribute grammar. And you can see that the semantic rules in an attribute grammar, they define the value of attribute purely in terms of values of other attributes and constants. Okay, so very simple point. In the attribute grammar, the semantic rules, they will compute the value of attribute in terms of the value of other attributes and constants. Okay, so you can see the semantic rules in attribute grammar define the value of attribute purely in terms of values of other attributes and constants. Okay, so you can see all the semantic rules are all about attributes, nothing else. Okay, so that is your attribute grammar. I hope you understood. Okay, so tell me, look at this SDD and tell me, is this attribute grammar? This structure, this is called SDD. SDD means context free grammar plus attributes plus semantic rules. So you can see that this is your SDD. Tell me, this SDD, is this attribute grammar? Yes, this is a attribute grammar because you can see all the semantic rules, they are computing the attribute values purely in terms of other attribute values and constants. Yes or no? This is what we have written here. You can see that an SDD without side effect is called attribute grammar. And you can see in the attribute grammar, all the semantic rules in attribute grammar define the value of an attribute purely in terms of values of other attributes and constants. Okay. So you can see here that all the semantic rules, they are defining the attribute values purely in terms of other attribute values and constants. So basically, all the semantic rules, they are computing the attribute values. Yes or no? There is no side effect here. We are not doing anything other than attribute computation. Yes or no? So this is attribute grammar. I can say this SDD is attribute grammar. This SDD is an attribute grammar. Okay, very simple. What about this SDD? Is this SDD attribute grammar? Tell me. This syntax directed definition, is this attribute grammar? Yes, this is also attribute grammar because you can see all the semantic rules, they are computing the attribute values in terms of other attribute values and constants. We are not doing anything other than attribute computation. So this is a SDD without side effects. There are no side effects here. Okay. So overall, I can say that yes, this SDD, this is also attribute grammar. This is an attribute grammar. Okay. Is this clear? Very simple. Now the next topic is synthesized and inherited attributes. And this is the most important topic, I can say, from the gate exam point of view. A lot of questions have come based on synthesized and inherited attributes. One more thing, there are a lot of misconceptions in these concepts. So what we will do a lot of practice. First we will understand the definition of synthesized attributes, inherited attributes, the correct definition we will understand. Then we will do a lot of practice. Okay, all the different varieties of questions we will do. So you will become master of synthesized and inherited attributes. So the next concept is synthesized attributes and inherited attributes. Let's see. So let's see synthesized and inherited attributes. Let me tell you, for any non-terminal, we have already seen that for any non-terminal, we have a finite set of attributes associated with it. Correct? Now let me tell you, some of these attributes are synthesized and the remaining attributes are inherited. Okay, very simple point that we shall deal with two kind of attributes for non-terminals, synthesized and inherited attributes. Okay, if you have any non-terminal, let's take a non-terminal. Let's assume we have a non-terminal A. Okay, now, or let's take the non-terminal, some non-terminal X. Okay, I am taking a non-terminal X. So let's assume that we have a non-terminal X. Now, we already know that with this non-terminal X, we have a finite set of attributes associated. Yes or no? Okay, so you can see that the finite set of attributes associated, the finite set of attributes associated with X, let's call it AX. Okay, so you can see the finite set of attributes associated with X. This we already know that with every non-terminal, a finite set of attributes are associated. So you can see, let's assume that the finite set of attributes associated with X is AX. Okay, AX means this is the finite set of attributes. This is the set of attributes associated with X. Okay, so you can see, let me write it here. Let the, okay. So very simple. Now let me tell you that in this AX basically, you can say, what is this AX? This is a set of attributes associated with X. Okay, now let me tell you, in these attributes, some attributes are synthesized and the remaining are inherited, and they are disjoint. Means for any non-terminal X, any attribute of X can be synthesized or it can be inherited, but not both. Okay, so let me tell you, this AX you can write as SX union IX. Okay, and let me tell you that SX intersection IX, that is basically empty. Okay, what is this SX? This is the synthesized attributes of X. And what is IX? These are the inherited attributes of X. Okay, is this clear? I hope you understood this point. Okay, see, very simple point. I already told you that with every grammar symbol, we have a set of attributes associated. Okay, that we have already seen. Here I am discussing for non-terminals. I will also tell you about terminals. Don't worry. Okay, after some time, I will also tell you about attributes of terminals. But right now, let's focus on attributes for non-terminals. Okay, so you can see, if you have a non-terminal X, then we already know that a finite set of attributes is associated with X. So let's assume that the attributes associated with X, that is AX. Then let me tell you that in these attributes which are associated with X, some attributes are synthesized and the remaining are inherited. And let me tell you, for any non-terminal X, the attributes, any attribute will be either synthesized or inherited, but not both. Okay, means for a non-terminal X, you cannot have same attribute which is both synthesized and inherited. Okay, either it will be synthesized or it will be inherited, but not both. Okay, is this clear? So this is what I'm saying, that AX means the attributes associated with X, that is equal to SX union IX. What is SX? These are the synthesized attributes associated with X. And what is IX? These are the inherited attributes of X. And remember, SX intersection IX, that is phi. Means for a non-terminal, same attribute can never be both synthesized and inherited. Either it will be synthesized or it will be inherited, but not both. Okay, is this point clear? So that is what I have written here. You can see an attribute of a non-terminal must either be synthesized or inherited, but not both. Okay, so you can read this here, that let ax be the set of attributes associated with non-terminal x. Then remember what this ax? This ax consists of two disjoint set. They can be possibly empty. Remember, it may be possible that this non-terminal x has no synthesized attribute. It may be possible. Maybe all the attributes of x are inherited. That is fine. Or all the attributes of x are synthesized. That is also fine. But the point is that an attribute of non-terminal, an attribute of any non-terminal must be either synthesized or inherited, but not both. Okay, so you can see, let ax be the set of attributes for non-terminal x. Then this ax basically contains two disjoint set, possibly empty, sx and ix. Sx is the synthesized attributes of x, and ix is the inherited attributes of x. Okay, so you can see a non-terminal may have some synthesized attributes, some inherited attributes, but each attribute of a non-terminal has exactly one role. Means any attribute of any non-terminal can never be both synthesized and inherited. Either it will be synthesized or it will be inherited, but not both. I hope this point is clear. Okay, now we will see the definition of synthesized and inherited. But so far, is this point clear? That for a non-terminal, same attribute can never be both synthesized and inherited. For a non-terminal, if you take any attribute, that will be either synthesized or it will be inherited, but not both. Okay, is this point clear? So you can see that for any non-terminal, the set of attributes you can divide into two categories: synthesized attributes, inherited attributes, and they are disjoint. Okay, is this clear? This is the first point. Now we will see the definition of synthesized attribute, inherited attribute, and we will see the most simple definition. And using that definition, a lot of questions, or I can say all the questions, you can solve. Okay, so this definition I found in one of the research paper. Okay, so let's see this definition. So you can see synthesized and inherited attribute, simplest definition we are going to see now. Okay, so just focus here. We already know that with each production, a set of semantic rules are associated. Okay, this we already know, that with every production, a set of semantic rules we associate. Okay, so now you consider a production A going to x1, x2, xn. So consider this production. Now let me tell you about the definition of synthesized attribute and the definition of inherited attribute. Remember, this is the production, and you already know that corresponding to every production, a set of semantic rules we write. Okay, so corresponding to this production also, we will write a set of semantic rules, correct? Okay, yes or no? This we already know, that corresponding to every production, a set of semantic rules we write. Okay, and in these semantic rules, what we do? In these semantic rules, we define the attributes. Yes or no? So we define the attributes of the grammar symbols in this production. Okay, so let me tell you that corresponding to this production, if I write a semantic rule in which I define an attribute of this A, this is the head and this is the body. Yes or no? So let me tell you, corresponding to this production, if I write a semantic rule in which I define any attribute of this LHS of this production, means I define any attribute of this A, then that will be called synthesized attribute. That's it. Okay, and also remember, corresponding to this production, if I write a semantic rule in which I define any attribute of any grammar symbol on the RHS, means I define any attribute of x1, or I define any attribute of x2, or I define any attribute of xn, means corresponding to this production, I write a semantic rule in which I define any attribute of any grammar symbol on the RHS, then that attribute will be called inherited. That's it. This is the definition. Synthesized attribute, inherited attribute. Okay, so again, let me repeat. Corresponding to this production, we will write a set of semantic rules. This you already know. Okay, with each production, a set of semantic rules are associated. So this is the production, and corresponding to this production, or I can say with this production, we will write a set of semantic rules. Now, in the semantic rule with this production, with corresponding to this production, I write a semantic rule. In this semantic rule, if I define any attribute of A, then that will be called synthesized attribute. And in this semantic rule, if I define any attribute of any grammar symbol on the RHS, then that attribute will be called inherited attribute. Okay, so let's see the definition here. You can see, corresponding to this production, with this production, a set of semantic rules will be associated, yes or no? So, corresponding to this production, if we write a semantic rule that computes or that defines an attribute of non-terminal on the LHS, means this A. If I write a semantic rule which computes or which defines any attribute of this LHS, then it is called synthesized attribute of A. Okay, if I define any attribute of this LHS A, then that attribute will be called synthesized attribute of A. Okay, and let's see the definition of inherited attribute. You can see, corresponding to this production, if we write a semantic rule which computes or which defines any attribute of a non-terminal X on the RHS, means if I compute any attribute of any non-terminal on the RHS, then that will be called inherited attribute of X. Okay, but there is one more last condition. What is that? When you define whether synthesized attribute or inherited attribute, when you define that attribute in the semantic rule, when you define that attribute, then remember that attribute you can define in terms of either constants or attributes of these symbols which are in this production. Means you cannot use any attribute of any symbol which is not present in this production. Okay, in this production, the symbols that are present, only their attributes you can use to define synthesized attribute or inherited attribute. Is this point clear? Okay, so let me write it here. You can see, in both cases, whether synthesized attribute or inherited attribute, in both cases, the semantic rule, or I can say the function, the semantic rule which defines the attribute of non-terminal n, can only use the attributes of any symbol in this production, including the attributes of n itself. For example, if I'm defining attribute of A, then I can use attribute of A also to define it. If I'm defining any attribute of x2, then I can use attributes of these grammar symbols, including attributes of x2, to define attribute of x2. Okay, so you can see, in both cases, synthesized or inherited, in both cases, the semantic rule which defines the attribute of non-terminal n can only use the attributes of any symbols in the production. You can use the attributes of any symbols in this production, including attributes of n and constants. Okay, that's it. I hope you understood this definition. Okay, let me just make it clear if you did not understand. Of course, we will take a lot of questions, but this is the simplest definition. Let me tell you. Very simple. Remember, you have a production A going to x1, x2, and so on, xn. This is the production. Okay, you already know that with every production we associate a set of semantic rules. Okay, some set of semantic rules, like rule number 1, rule number 2, rule number 3, like that. Okay, yes or no? So you can see that with every production, a set of semantic rules are associated. Now, in these semantic rules, what we do? In these semantic rules, we compute the attributes of the grammar symbols present in this production. Yes or no? Using these semantic rules, we compute the attributes. We compute the attributes of the grammar symbols present in this production. Now let me tell you, if I write a semantic rule corresponding to this production, I write a semantic rule in which I compute or I define any attribute of this LHS, then that attribute will be called synthesized attribute of this LHS. And remember, corresponding to this production, if I write a semantic rule in which I define or I compute any attribute of any non-terminal on the RHS, I define any attribute of any non-terminal on the RHS, then that attribute will be called inherited attribute of that grammar symbol. Okay, inherited attribute of that non-terminal. I hope you understood. So very simple. Corresponding to this production, if I write a semantic rule which computes attribute of LHS, that will be called synthesized attribute of LHS. And if I write a semantic rule which computes attribute of any non-terminal on the RHS, then that will be called inherited attribute of that non-terminal. Okay, this is the simple definition, nothing else. Okay, now we are going to do a lot of practice. You answer all the questions that I am going to solve now. Let's take this SDD. This is the syntax directed definition, and these are the grammar symbols B comma D. These are the non-terminals. We need to find what are the synthesized attributes associated with these grammar symbols, and we need to find what are the inherited attributes associated with these non-terminals. Okay, basically for B comma D, what are the synthesized attributes, what are the inherited attributes we need to find. Okay, already we already know one thing. Remember, for any non-terminal, the synthesized attributes and inherited attributes, they will be disjoint. Okay, and for this D also, for any non-terminal, remember, the synthesized attributes and the inherited attributes, they will be disjoint. Okay, this we already know, this we have already seen. Okay, now let's see here. Let's find for non-terminal B what are the synthesized and inherited attributes. For non-terminal D, what are the synthesized and inherited attributes. Okay, so what we will do, let's go production by production. Let's focus on this production. In this production, what is LHS? LHS is B. And what is RHS? RHS is D comma B. Remember this B1, this is also variable B. This B1 is also variable B, but these are different instances of same variable. Okay, so here you can see that LHS is B. Now notice this semantic rule, you notice. Tell me in this semantic rule, which attribute we are defining, which attribute we are computing, tell me. We are computing attribute of LHS. Do you agree with me? Corresponding to this production, consider this semantic rule. You can see in this semantic rule, we are computing attribute of LHS. And I told you that corresponding to any production, if you write a semantic rule which computes, which defines attribute of LHS, then that attribute will be called synthesized attribute of LHS. Is this clear? Let me know. Please tell me. You can notice in this semantic rule, we are defining, in this semantic rule, we are defining, or I can say we are computing b.pos. Okay, yes or no, we are computing b.pos, and you can see this B, this is the LHS. Okay, so you can see that corresponding to this production, this semantic rule that we have written, in this semantic rule we are defining, we are computing attribute of LHS. So this attribute will be called synthesized attribute of B. So remember, for this B, POS is synthesized attribute. Please tell me, did you understand? Very simple definition, nothing else. Okay, slowly you will love this definition, let me tell you. Okay, simplest definition. You are going to love this definition because a lot of practice we are going to do. Okay, did you understand this? Now let's see the next. You can see for this production, this is another semantic rule. In this semantic rule, can you tell me which attribute we are defining? We are defining b.val, and you can see this B, this is the LHS. Again, you can see in this semantic rule, we are defining attribute of LHS. And I told you that corresponding to any production, in a semantic rule, if you define, if you compute attribute of LHS, then that attribute will be called synthesized attribute of LHS. Okay, yes or no? So here you can see this VAL. This is a synthesized attribute of B. Is this clear? Let's see the next. Tell me the next. You can see with this production, we have another semantic rule associated. Actually, with this production, three semantic rules are associated. So you can see with this production, this is another semantic rule. In this semantic rule, can you tell me which attribute we are computing, which attribute we are defining? You can see we are defining d.pow, and you can see this d, this is non-terminal on the RHS. So you can see that corresponding to this production, we have written this semantic rule in which we are defining, we are computing attribute of a non-terminal on the RHS. So tell me, this attribute will be called what? This will be called inherited attribute of that non-terminal. So you can see for this D, this POW is inherited attribute. Tell me, did you understand or not? Let me know. One by one, we are checking the semantic rules, nothing else. Okay. So let's see the next. Let's see here. What about this production? Consider this production. You can see corresponding to this production, these are the semantic rules. In this semantic rule, which attribute we are defining? We are defining POS attribute of LHS. And I told you, corresponding to any production, if I write a semantic rule which defines, which computes any attribute of LHS, then that attribute will be called synthesized attribute of LHS. So you can see here, you are computing POS attribute of LHS. So this POS will be synthesized attribute of LHS. So you can see that for this B, this POS is synthesized attribute. We have already written. Okay, yes or no? Now let's see the next. You can see here also, you can see that in this semantic rule, we are defining, we are computing an attribute of LHS. Yes or no? This B dot val, this is B. So you can see we are defining, we are computing an attribute of LHS. So this attribute will be called synthesized attribute of LHS. So you can see this VAL, this is synthesized attribute of B. We have already written. Okay. And you can see here d dot POW equal to 0. So you can see in this semantic rule, which attribute we are defining? Tell me. Corresponding to this production, this semantic rule we have written in which we are computing, we are defining an attribute of a non-terminal on RHS. Yes or no? Here you are computing an attribute of a non-terminal on RHS. So this attribute will be called inherited attribute of that non-terminal. Yes or no? So you can see that this POW, this is an inherited attribute of D. We have already written. Okay. Let's move on. So you can see this we have already seen. Okay. What about this D dot val? Can you tell me? This D dot val, you can see corresponding to this production, this is the production. Corresponding to this production, this semantic rule we have written. In this semantic rule, we are defining, we are computing an attribute of LHS. I told you that corresponding to any production, if you write a semantic rule in which you are computing, you are defining an attribute of LHS, then that will be called synthesized attribute of LHS. So VAL, this is synthesized attribute of D. Yes or no? So remember for D, this VAL is a synthesized attribute. Okay. And you can see this last one also. Look at this. This is the production where D is LHS. Okay. So you can see here, corresponding to this production, this semantic rule we have written. And in this semantic rule, we are defining, we are computing this attribute of LHS. Yes or no? D is LHS. And you can see we are computing D dot val. We are defining an attribute of LHS. So this attribute will be called synthesized attribute of LHS. Yes or no? So you can see for this D, this VAL, this is synthesized attribute. Okay, that's it. I hope you understood. Please tell me, is this clear? This definition. Basically, what you need to do, you just need to see in these semantic rules which attribute you are defining. Is this attribute of LHS? Is this attribute of a non-terminal on the RHS? That's it. This is what you need to check. Okay. For example, let me quickly do actually the same question. Let me quickly do. You can see what I need to do. I just need to check in these semantic rules which attribute I am defining. In these semantic rules, see, these are the semantic rules. In these semantic rules, which attribute I am defining. I just need to see these attributes. These are attributes of LHS or these are attributes of a non-terminal on the RHS. So you can see here in this semantic rule, this b dot pos I am defining, and this is attribute of LHS. So this is synthesized attribute. Next, you can see in this semantic rule, we are defining b dot well. This is attribute of LHS. So this is synthesized attribute. You can see in this semantic rule, we are defining an attribute of RHS. Yes or no? This d dot POW, and you can see this d is on the RHS. So in this semantic rule, we are defining attribute of a non-terminal on the RHS. So this is inherited attribute. Okay, here you can see that this POS, this is synthesized attribute because here you are defining this attribute of LHS. Okay, here you are defining the attribute of LHS. You can see here you are defining the attribute of RHS. Okay, so this is inherited attribute. Here you are defining attribute of LHS. So this is synthesized attribute. Here you are defining attribute of LHS. So this is a synthesized attribute. Isn't it simple? Tell me, what do you think? This method, this definition, very easily you can check. Okay, so you can see finally this is your answer for this question. Let's take this SDD, and in this SDD, let's find for each non-terminal what are synthesized attributes and what are inherited attributes. Okay, so let's see. You can see this is the SDD. On one side, let me write the non-terminals. Okay, on one side non-terminals I am writing. On one side, let me write synthesized attributes. And here let me write inherited attributes. Okay, so let's see. Tell me, for this non-terminal L, you can see these are the non-terminals. Okay, for this non-terminal L, what are the synthesized attributes? What are the inherited attributes? For this non-terminal E, for this non-terminal T, and for this non-terminal F. Okay, so tell me quickly. The method I told you is very easy. What you need to do to find what are the synthesized attributes of a non-terminal and what are the inherited attributes of a non-terminal, what you need to do, you just check the semantic rules. In the semantic rules, you check which attributes you are defining or which attributes you are computing. Okay, and then you see that attribute is attribute of LHS or that attribute is attribute of RHS. If that attribute is attribute of LHS, then that is synthesized attribute. If that attribute is attribute of RHS, then that is inherited attribute. Okay, it's very simple, easy peasy. Okay, so you can see here, let's consider this semantic rule corresponding to this production. This is the semantic rule. So in this semantic rule, which attribute we are defining? We are defining L dot well. This is attribute of LHS. So this is synthesized attribute. Is this clear? So you can see for this non-terminal L, this VAL is a synthesized attribute. Okay, very simple. Now let's see the next. For this production, corresponding to this production, this is the semantic rule associated. And you can see in this semantic rule, which attribute we are computing, which attribute we are defining. We are defining E dot well. And you can see this E dot well, this is E, this is even, remember. Okay, you can see. So E dot well, so this is attribute of LHS. So this is a synthesized attribute. So this is synthesized attribute of E. Is this clear? So you can see for E also, this well is synthesized attribute. Okay, very simple. Let's see the next semantic rule. In this next semantic rule, which attribute we are computing? We are defining E dot well. and this is attribute of LHS, yes or no? So in this production, E is LHS, T is RHS. So you can see this E dot val, this is attribute of LHS. So this is synthesized attribute. So you can see for E, for this non-terminal E, VAL is a synthesized attribute. We have already written. Okay. Now let's see the next. You can see corresponding to this production, this is the semantic rule associated. And here you can see this T dot val we are computing. We are defining T dot val, and this is attribute of LHS, yes or no? Remember, this is T1, this is T. So here you are defining, you are computing T dot val. So this is attribute of LHS. Okay, you are computing, you are defining attribute of LHS. So this attribute is synthesized attribute. So you can see for this non-terminal T, VAL is a synthesized attribute. Okay, very simple. Now let's see the next. Corresponding to this production, for this production, this is the semantic rule associated. And you can see in this semantic rule, which attribute we are computing, which attribute we are defining T dot val. And this is attribute of LHS. This, yes or no, we are computing, we are defining attribute of LHS. So this attribute is synthesized attribute, yes or no? I can say VAL, this is synthesized attribute of T. Okay, so you can see for T, this VAL, this is synthesized attribute. Okay, yes or no? Now let's see the next. For this production, this is the semantic rule associated, and you can see we are defining F dot VAL. You can see this attribute that you are defining, that you are computing, this is attribute of LHS. Okay, so you are computing attribute of LHS. So this attribute is a synthesized attribute of F. Means for this F, VAL is a synthesized attribute. Okay, and you can see finally here for this production, this is the semantic rule associated, and you can see here what you are defining, what you are computing. You are computing F dot val. Okay, and you can see this F dot val you are computing. This attribute is attribute of LHS, yes or no? You are computing attribute of LHS. So this is synthesized attribute. This VAL, this is synthesized attribute of F. Okay, you can see VAL, this is synthesized attribute of F. So in this particular SDD, you can notice that there is no inherited attribute. Yes or no? Is this clear? So you can note that in this SDD, in this SDD, no inherited attribute. In this SDD, we have no inherited attribute. Okay. All are synthesized attributes. Yes or no? All are synthesized attributes. Is this point clear? Let me know. Did you understand? Very simple, right? Let's consider this SDD. Now, for this SDD, for all the non-terminals, we need to find what are the synthesized attributes, what are the inherited attributes. Okay, the same definition you need to apply. What you need to do? Corresponding to every production, you check the semantic rules, and you check in this semantic rule, basically in these semantic rules, what are the attributes that you are computing, you are defining, and then you see that attribute is attribute of LHS or that attribute is attribute of RHS. Means you are defining attribute of LHS or you are defining attribute of RHS. If you are defining attribute of LHS, that attribute will be called synthesized attribute. And in any semantic rule, if you are defining any attribute of RHS, then that will be called inherited attribute of that non-terminal. Okay, is this clear? This is the simple definition, the simplest definition of synthesized attribute, inherited attribute, and you can just apply it. Okay, so let's see. You can see this is the SDD, and in this SDD, on one side, let me write the non-terminals. Let me write on one side non-terminals. Okay, on one side, I'm writing the non-terminals. Here, let me write the synthesized attribute. Okay, and here, let me write the inherited attributes. Okay, what are the inherited attributes, what are the synthesized attributes, and here I am writing all the non-terminals. What are the non-terminals? P is non-terminal, L is non-terminal, L1 is non-terminal. Notice one thing here, L comma L1 are different non-terminals. Okay, please understand here. L comma L1, they are different non-terminals. And here you can see that L1 comma L2, they are basically same, means they are basically L1, or I can say that this L1 comma L2, they are different instances of same variable L1. But here remember, L comma L1, they are different variables. Okay. So very simple. So you can see these are the variables. These are the different variables. So B, L, L1, N. Okay, that's it. So, okay, that's it. So these are the non-terminals. Now let's see what are the synthesized attributes of non-terminals and what are the inherited attributes of these non-terminals. Okay. So you tell me one by one, you are going to tell me. So let's check all the semantic rules, which attributes they are defining. If they are defining attribute of LHS, then that is synthesized attribute. If they are defining attribute of RHS, then that will be inherited attribute. Very simple definition. Yes or no? One line definition. You check the semantic rule. If the semantic rule is defining an attribute of LHS, then it is synthesized attribute. If semantic rule is defining an attribute of RHS, it is inherited attribute. Very simple, very easy definition. Okay, nothing else. So let's see this. You can see here, look at this semantic rule corresponding to this production. For this production, this is the semantic rule associated. So here you can see, for this B, this is the attribute V. Okay, for this B, this is the attribute V. Let me tell you here. Okay, what this actually means, let me tell you. So this is same as B dot V. Okay, you can also write it B dot V. Is this clear? B dot V means attribute V of B. Means attribute V of B. Okay, very simple. So let's see here. Which attribute you are defining? Is that attribute of LHS or is that attribute of RHS? So you can see in this semantic rule, we are defining attribute V of B. And you can see this B, this is LHS. So we are defining attribute of LHS. So this attribute will be synthesized attribute of LHS. Means for this B, this V is a synthesized attribute. Okay, for this B, this V is a synthesized attribute. Is this clear? Very simple, right? Okay, let's see the next. Let's see this. Now, here you can notice again. Okay, look at this semantic rule. In this semantic rule, we are defining attribute V of B. And you can see B is on the LHS. So we are computing attribute of LHS. So this will be synthesized attribute of LHS. Means this V, this is synthesized attribute of LHS we have already written. For this B, this V is a synthesized attribute. Okay, very simple. So this is done. This is done. Okay, let's see the next. Now notice, corresponding to this production, in this production, for this production, LHS is L, RHS is B. Okay, notice that we have multiple semantic rules corresponding to this production. We have this semantic rule, we have this semantic rule, and we have this semantic rule. Okay, is this clear? For this production, three semantic rules are associated with this production. Is this clear? And for this production, LHS is L and RHS is B. So remember, in these semantic rules, if you are defining an attribute of LHS, that attribute will be synthesized attribute. In these semantic rules, if you are defining any attribute of B, then that will be called inherited attribute. Okay, is this clear? In these semantic rules, if you are defining any attribute of L, that will be synthesized attribute of L. In these semantic rules, if you are defining any attribute of B, that will be inherited attribute of B. Okay, is this clear? So you can see, look at this semantic rule. In this semantic rule, you are defining attribute of L, attribute V of L. So I can say we are defining attribute of LHS. So this is synthesized attribute of L. So this V is a synthesized attribute of L. For this L, this V is a synthesized attribute. Okay, let's see the next. You can see in this semantic rule, we are defining attribute of B, attribute S of B. Okay, you can see here what this means. This is same as, remember, this is same as B dot S. Okay, means attribute S of B. So notice that here we are defining attribute S of B. B is on the RHS. So we are defining attribute of RHS. So this attribute is inherited attribute of B. Is this clear? So for this B, S is inherited attribute. For this B, S is inherited attribute. Okay, is this clear? Let's see this semantic rule. In this semantic rule, we are defining attribute of L. L is on the LHS. So you can see we are defining attribute of LHS. So this attribute is synthesized attribute of LHS. So I can say for this capital L, small l is synthesized attribute. For this capital L, small l is synthesized attribute. Okay, very easy. Now let's see the next. Let's see this production. You can see for this production, 4 semantic rules are associated with it. Okay, yes or no? So you can see for this production, we have this semantic rule, we have another semantic rule, we have another semantic rule, and we have another semantic rule. Okay, so now let's see. Notice one thing. In this production, LHS is L1 and RHS is L2 comma B. Okay, so if you are defining in these semantic rules, if you are defining any attribute of L1, that will be synthesized attribute of L1. And in these semantic rules, if you are defining any attribute of B or any attribute of L2, then that will be inherited attribute of B or L2. Okay, is this clear? So let's see. In this semantic rule, we are defining attribute of L1, means we are defining attribute of LHS. So this will be synthesized attribute of L1. So for this L1, this V is a synthesized attribute. For this L1, V is a synthesized attribute. Okay, is this clear? Very simple, right? Now let's see this semantic rule. In this semantic rule, we are defining attribute of B. Yes or no? Attribute S of B. We are defining attribute S of B. B is on the RHS. So we are defining attribute of RHS. So this is inherited attribute of B. Is this clear? For B, S is inherited attribute. For B, S is inherited attribute. We have already written. Okay. Let's see the next semantic rule. In this next semantic rule, we are defining attribute of L2. Attribute S of L2. Yes or no? Attribute S of L2. So we are defining attribute of L2. L2 is on the RHS. We are defining attribute of RHS. So this is inherited attribute of L2. So for L2, S is inherited attribute. Okay, for L2, S is inherited attribute. Is this clear? Now, there is no L2 here. Yes or no? There is no L2. Why there is no L2? Because please understand, I told you this point that L1 comma L2 are basically same. They are different instances of same variable. Okay, yes or no? Notice one thing here, that L2 and L1 are basically same. L2 comma L1 are basically same. L2 L1 are same variable, different instances. Same variable, different instances. Different instances. Okay, is this clear? So let's come back to this point. Look at this semantic rule. In this semantic rule, we are defining attribute of L2. L2 is on the RHS. We are defining attribute of RHS. So this is inherited attribute of L2. But L2 comma L1 are basically same. So I can say that this S is inherited attribute of L1. Is this clear? For this L1, S is inherited attribute. Okay, is this clear? Because L1 comma L2 are basically same variable, different instances. I hope you understood this point. So you can see this S, this is inherited attribute of L1. Clear? Let me know. Okay, if you are confused, then you can simply write like L2 here. Okay, you can write L2 here. Then you can see that this S is inherited attribute of L2. Okay, is this clear? So if you don't want to get confused, then you can simply write like L2 here. Okay, very simple. But I hope you understood the point, what I'm trying to say. Okay, so let's forget about the, okay, just simply write L1 because this is the non-terminal. Okay, now let's see the next. What about this semantic rule? In this semantic rule, we are defining attribute of L1. L1 is on the LHS. We are computing attribute of LHS. So this is synthesized attribute. So for this capital L1, this small l is synthesized attribute. For this capital L1, this small l is synthesized attribute. Okay, very simple. Now let's see the next production. For this production, these semantic rules are associated. This semantic rule, this semantic rule. Okay, so let's see. You can see here in this production, the LHS is capital N and the RHS is L. Okay, so you can see in these semantic rules, if I define any attribute of N, then that will be synthesized attribute. If I define any attribute of L, that will be inherited attribute of L. Okay, so you can see in this semantic rule, I'm computing attribute of LHS, attribute of capital N. So you can see this will be synthesized attribute of N. So for N, this V is synthesized attribute. Okay, now let's see this. In this semantic rule, we are defining, we are computing attribute of L, attribute S of L, and this L, this is on the RHS. So you are computing attribute of RHS. So this is inherited attribute of L. Is this clear? So for this capital L, this S is inherited attribute. So for this capital L, this S is inherited attribute. Okay, very simple. Now let's see the next. You can see this is the production, and for this production, with this production, these are the semantic rules which are associated. Okay, so let's see these semantic rules. Remember, in this production, the LHS is the LHS is N, and the RHS is L1 L2. Remember, L2 is same as L1. Yes or no? L2 is same as L1. This I told you that L2 L1, they are basically same variable, different instances. Okay, to differentiate between them, we are using this L1 L2 like that. Okay, so basically they are same variables, different instances. Okay, so let's see here. You can see in this semantic rule, we are defining an attribute of LHS. This capital N, this is on the LHS. So you can see that we are defining this attribute V of N. So this is synthesized attribute of N. So for this N, this V is synthesized attribute. Okay, we have already written. Now let's see this semantic rule. In this semantic rule, we are computing attribute of L1. And you can see this L1 is on the RHS. So you can see we are we are defining attribute of RHS. So this is inherited attribute of L1. So for L1, S is inherited attribute. For L1, S is inherited attribute we have already written. Look at this semantic rule. In this semantic rule, we are defining attribute of L2. Okay. You can see L2 is on the RHS. So we are defining attribute of RHS. So this is inherited attribute of L2. L2 comma L1, they are basically same variable, different instances. So I can say for L1, this S is inherited attribute. Okay. For this L1, S is inherited attribute. Okay, that's it. So this is the final answer. Please tell me, did you understand? Let me know. Easy peasy. Do you agree with me that these things are very easy? The definition that we have seen for synthesized attribute, inherited attribute, this is the most simple definition. I hope you understood. Let's see this example. See, a lot of practice we are doing. All these questions I have taken from the standard universities, from the research papers, from many resources. I have collected these questions for your practice. So I hope you understood. Let's consider this SDD. In this SDD, for all the non-terminals, let's find what are the inherited attributes and what are the synthesized attributes. Okay, so you can see this is our SDD, and on one side I will write non-terminals. Okay, on this column, let me write the synthesized attributes. And here, let me write the inherited attributes. Okay. Let's see. So what are the non-terminals? You can see the non-terminals are B, L, L1, N. You can see this L comma L1, they are different non-terminals. Okay. But you can see this L1, L2, they are basically same variables, different instances. Here also L1, L2, same variables, different instances. Okay. So you can see here that L1, L2, same variables, different instances. Okay. So let's see all the semantic rules, which attribute they are defining, which attribute they are computing. Is that attribute of LHS? Is that attribute of RHS? Any semantic rule, if it is computing any attribute of LHS, that will be synthesized attribute of LHS. If any semantic rule is computing any attribute of a non-terminal on the RHS, then that will be called inherited attribute of that non-terminal. Okay, that is the definition. Now we can easily solve this question. So you can see, consider this semantic rule. In this semantic rule, we are defining attribute of B. B is on the LHS. So basically we are defining attribute of LHS. So this is synthesized attribute of LHS, means for this B, this V is a synthesized attribute. Okay, for this B, this V is a synthesized attribute. This V. Okay, very simple. So here also the same thing, that this VB we are defining, and this B, this is on the LHS. So you can see that this is the attribute of LHS that we are defining. So this is a synthesized attribute. Okay, so this V is a synthesized attribute of capital B. Very simple. Now let's see these semantic rules for this production. In this production, the LHS is L, the RHS is B. So you can see in these semantic rules, if you define any attribute of L, then that will be called synthesized attribute of L. If you define any attribute of B, that will be called inherited attribute of B. So you can see here you are defining attribute of L. Here also you are defining attribute of L. So these are basically synthesized attributes of L. So you can see V comma small l, these are synthesized attributes of capital L. Okay, very simple. Let's see these semantic rules for this production. Again, you can see here the LHS is L1 and the RHS, that is L2 comma B. So if you define in the semantic rules, if you define any attribute of L1, that will be called synthesized attribute of L1. And in the semantic rules, if you define any attribute of B, that will be called inherited attribute of B. In these semantic rules, if you define any attribute of L2, then that will be called inherited attribute of L2. But L2 and L1 are basically same, so I can say inherited attribute of L1. Okay, I hope you understood this point. So you can see here in this semantic rule, attribute of L1, we are defining L1 is on the LHS. In this semantic rule also, we are defining attribute L of L1. L1 is on the LHS. So you can see in these semantic rules, we are defining attribute of LHS. So these are synthesized attribute of LHS. So you can see for L1, this V comma L, these are the synthesized attributes. Let's see the next. For this production, this is the semantic rule. And in this semantic rule, we are defining attribute V of N. N is on the LHS. So you can see here, attribute of LHS we are defining. So it is a synthesized attribute of LHS. Means for this capital N, this V is synthesized attribute. Okay. Let's look at this semantic rule. In this semantic rule, we are defining attribute V of N. N is on the LHS. So we are defining attribute of LHS. So this is synthesized attribute of LHS, means for this N, this V is a synthesized attribute. Okay. So that's it. So you can see finally in this SDD also you can notice that we don't have any inherited attributes. All the attributes are synthesized. Okay. Is this clear? So you can note that in this SDD, all attributes are synthesized. All attributes are synthesized. There is no inherited attribute in this SDD. Okay, I hope you understood. Let's solve GATE 2019 question based on synthesized attribute, inherited attribute. Already a lot of practice we have done, so I have full confidence on you that you can solve it very easily. So let's read this question. Consider the following grammar and semantic actions to support the inherited type declaration attributes. The question is saying that we have inherited type declaration attributes, means we have inherited attributes. All the attributes are inherited attributes. For example, this type attribute, you can see type declaration attribute. You can see this type attribute, this is basically inherited attribute. Okay. The question is saying that inherited type declaration attribute means this type attribute that you have, this is a inherited attribute. Okay. Now the question is saying let x1, x2, x3, x4, x5, x6 these be placeholders for non-terminals DTL L1 in the following table. Remember here, this L comma L1, actually this L comma L1, they are basically same variable, different instances. If you see what are the different non-terminals, then these are basically DTL. Okay. Now the question is saying x1 to x6, these are placeholders for non-terminals DTL L1. Okay. Remember L comma L1, they are same variables, different instances. Okay. Now this table is given to you where your production rules and the semantic actions, where this type attribute, this is an inherited attribute. The question is saying which one of the following are appropriate choices for x1, x2, x3, x4. We need to see for x1 to x4 what are the appropriate choices. This is a very easy question. Already we have seen what is inherited attribute, what is synthesized attribute, and the easiest definition we have already seen. Okay, what was the definition? Let me just recall, let me just revise. So you can see, we already know that with every production, we associate a set of semantic rules. So let's consider this production A going to x1, x2, xn. This is the production. Now remember, corresponding to this production, if we write a semantic rule in which we define any attribute of LHS, any attribute of A, if we define, then that will be called synthesized attribute of A. Now, let's see the definition of inherited attribute. You can see, corresponding to this production, if we write a semantic rule in which we define any attribute of any non-terminal on the RHS, then that attribute will be called inherited attribute of that non-terminal. And one more important note, that is when you compute, when you define the attribute, then remember to define that attribute, you can only use the attributes of these these symbols in this production. Okay, means you cannot use any attribute of any symbol which is not present in this production. Okay, very simple point I am saying, that whether you have inherited attribute or synthesized attribute, corresponding to this production, if I write a semantic rule to compute a synthesized attribute or to compute an inherited attribute, then remember that computation must be in terms of, must be only in terms of attributes of these symbols in this production. Okay, so you can read this, that in both cases the semantic rule which defines the attribute of non-terminal n can only use the attributes of any symbol in this production. You can use attributes of A, attributes of x1, x2, and so on, attributes of xn, including the attributes of n itself. For example, if you are defining attribute of x2, then to define, to compute attribute of x2, you can use attribute of A, attribute of x1, attribute of x2, attribute of xn, and so on. Okay, you can also use constants. So remember, if you are defining attribute of x2, then you can use attribute of x2 also. Okay, if you are defining attribute of x2, you can use attribute of any of these symbols. Okay, is this clear? Very simple point. I hope you understood. You can also use constants. Okay, so this is the definition of synthesized attribute, inherited attribute. This is the simplest definition. A lot of practice we have already done, so you are already expert of inherited attribute and synthesized attribute. Okay, so let's solve this question now. The question is saying that this type attribute, this is basically inherited attribute. Okay, so you can see the question is saying, it is given in the question that each semantic action defines or computes inherited attribute. Okay, because you can see that this type attribute, this is basically inherited attribute. Okay, so all these semantic actions, if you see, okay, notice that these two semantic actions, if you notice, these are side effects. Okay, do you agree? Look at look at these two semantic rules. Look at these two semantic rules. These two semantic rules, they are adding the type information in the symbol table. Okay, here you can see what we are doing. We are we are adding type information in symbol table. Okay, in symbol table. So remember, these are basically side effects. Okay, yes or no? I told you the definition of side effect. Side effect means if you do anything other than computation of attributes, then that is side effect. Okay, so you can see these are basically side effects. Okay, and you can see this is a SDD with side effect. So this is SDD. Yes, this is SDD, but this is not attribute grammar. Okay, yes or no? What is attribute grammar? Attribute grammar is SDD without side effects. So this is not attribute grammar. Okay, this is just extra information that I told you. Now let's come back to question. You can see in this question, the attributes that you are computing, the attributes that you are defining, that is type attribute, and the type attribute is inherited attribute. So you can see that all the semantic actions, they are basically defining inherited attribute. Okay, yes or no? So it is given in the question that each semantic action defines or computes an inherited attribute, and that inherited attribute is basically type attribute. Okay, very simple. Now tell me few things. Look at this semantic action. In this semantic action, if I tell you that this is inherited attribute, then can this x1 be d? Tell me, what can you say? Let me know. Notice, just focus on this semantic action. Okay, just focus on this semantic action corresponding to this production rule. Okay, this is the production rule. This is the production rule. For this production rule, this is the associated semantic action. Okay, we have this associated semantic action. X1 dot type is equal to, basically we are assigning x2 dot type in x1 dot type. Okay, so tell me one thing here. Can this x1 be d? Remember, if this x1 is d, then what will happen? Then you are defining attribute of LHS, so it will be synthesized attribute. Yes or no? I told you that corresponding to any production, if you write a semantic rule in which you define attribute of LHS, then that will be synthesized attribute. But we are already saying, the question is already saying that each semantic action is basically computing inherited attribute. So definitely this x1, this is either T or L. Do you agree with me? If this is a, if this type attribute, if this is inherited attribute, means in this semantic action, if you are computing inherited attribute, it simply means that this is attribute of a non-terminal on the RHS. So one thing you can guarantee, that this x1, either it will be T or it will be L. Okay, is this clear? But remember, x2 can be anything. I don't know about x2. X2 can be T, or it can be L, or it can be D. Is this clear? Please tell me. But one thing is sure, that x1 will be either T or L. Okay, because if x1 is D, then in this semantic action, we are computing an attribute of LHS, so it will be synthesized attribute. But the question is saying that this type attribute is inherited attribute. Okay, so x1 is definitely T or L. Okay, so you can see, let's see which option you can eliminate. X1 is T or L. X1 is T or L. So actually no option we can eliminate right now. Is this clear? So far I can say from the first semantic action, this is what we can say that X1 is T or L. And remember X2, this X2 will be either D or T or L. Okay, clear? Now let's see the next. Let's see the next production and the associated semantic action. Here actually we don't have any X1 to X4. Okay, so from here we will not get any information about X1 to X4. Notice that these two here, in these two semantic rules, we don't have X1 to X4. So actually this part is irrelevant to our question. What the question is asking, to that this part is irrelevant. But here I think there is some mistake, because notice one thing, for this production rule, this is the associated semantic action, and here we are defining this type attribute of LHS. Okay, we are defining in this semantic action, we are defining this attribute type of LHS. So here basically this type, this is a synthesized attribute of capital T. Okay, for this capital T, this type is a synthesized attribute, not inherited attribute. Okay, the same thing here also you can see. Here also you can see that for this production, this is the associated semantic action. And in this semantic rule, we are defining this attribute type of LHS. So this attribute type is synthesized attribute of this LHS-T. Okay. So I think there might be some mistake in this question, or maybe the question want to say only for these two statements. Okay. Basically, only for these two semantic action, maybe the question want to say that these are inherited attribute computation. Okay, means this one. Okay, maybe the question want to say that here we have inherited attribute computation. Okay, so anyway, this part is actually not relevant to what the question is asking. So let's just go to the this part. Okay, so you can see here we have production. L goes to L1 comma id. Remember one thing, that L comma L1, they are basically same variable, different instances. Okay, remember L comma L1, they are same variables, different instances. Okay, different instances. Same variables, different instances. So let's see here. We are saying that for this production, this is the associated semantic action, semantic rule. So here we have x3 dot type. To this we are assigning x4 dot type. Okay, so you can see we are saying that we are computing inherited attribute here. If you are computing inherited attribute here, can this x3 be L? Tell me, this x3, can it be L? No, it cannot be L, because if this x3 is L, then you are computing an attribute of LHS, so it will be synthesized attribute. Yes or no? So notice one thing, that definitely this x3 cannot be L. Okay, this is one thing, that x3 cannot be L. I can say that this x3, what it can be? X3 can be either L1 or ID. Okay, but the question is already saying that X3 is a placeholder for a non-terminal. Remember, the question is already saying that X1 to X6, these are placeholders for non-terminals. Okay, X1 to X6, these are placeholders for non-terminals. So, so remember, this X3 is definitely L1. Okay, yes or no? X3 is definitely L1. This is the point. And what can I say about X4? What can I say about X4? Remember, X3 is definitely L1, because if this is a computation of inherited attribute, then the attribute that you are defining, this should be attribute of RHS. On the RHS, we only have one non-terminal, that is L1. So X3 must be L1, because the question is saying that X1 to X6, these are placeholders for non-terminal. So X3 cannot be ID. X3 must be L1. Okay. Now let's see what about this x4. What this x4 can be? Remember, this x4 can be either L or it can be L1. Yes or no? X4 can be either L or it can be L1. Is this clear? Now, if this x4 is L1, x3 is already L1, x3 is already L1. If this x4 is also L1, then it will become redundant. Yes or no? Like L1 dot type is equal to L1 dot type. So it will become meaningless. I can say L1 dot type is equal to L1 dot type. It will become meaningless. Okay. But I can say it will become meaningless, but that's fine, because let me tell you, if you check the option C, if you check the option C, in this option C, you can notice that x1, x2 both are L. Option C is not the answer, but notice one thing, that in this option C, x1, x2 both are L. So if this option C is saying x1, x2 both are L, then you can see this will become L dot type equal to L dot type. Yes or no? Okay, if I put x1, x2 both are L, then this will become L dot type is equal to L dot type. So that will become meaningless. Okay, so I think that because of this option C, I think that the question maker is fine with meaningless thing. I can say meaningless computation. Okay, meaningless thing. So overall, I can say that this x4, either it can be L or it can be L1. Remember one thing, that this x4 can never be T. Yes or no? Because if you remember this point, I told you that whether you have synthesized attribute or you have inherited attribute corresponding to any production, when you write a semantic rule to compute synthesized attribute or to define inherited attribute, then remember, in this semantic rule we can use attribute of the symbols of this production only. Okay, you can see we can only use attributes of these grammar symbols in this production only. Okay, we cannot use attribute of any symbol which is not present in this production. Okay, so here you can see that in this production we don't have T. Do you agree? In this production we don't have T. So here, in this semantic rule corresponding to this production, in this semantic rule we cannot use any grammar symbol which is not present in this production. We can only use the attributes of the grammar symbols present in this production. So you can see this x4 can be either L1 or it can be L, but it can never be T. It can never be D. Yes or no? X4 can never be D. I hope you understood this point. So finally, what is the conclusion after our analysis? Finally, what we have found? We have found that this is what we have found from our analysis, that x1 is either T or L. Okay, this x1, this is either T or L. This x2, this is either T or L or D. Okay, x2 is T or L or D. Also, we have seen that this x3 is definitely L1. Also, we have seen that this x4 is either L or L1. Okay, you can notice that x4 cannot be T, x4 cannot be D. Okay, so this is the overall information that we can find from this given question, from this given paragraph. Okay, now finally the question is asking which is the most appropriate choice for x1 to x4. So you can see that option elimination we can use. Okay, notice that here you are saying x4 is T, x4 is T, x4 can never be T, x4 can never be D. So you can see these options are gone. Okay, these options are gone. Next, you can see that x3 must be L1, but in this option x3 is T, so that is also gone. Okay, so finally the answer will be option A. You can see x1 is L, x1 is L, x2 is T, x2 is T, x3 is L1, and x4 is L. Okay, so you can say the question is asking most appropriate choice, the question is asking, so answer will be option A. But of course, there can be other possibility also, because this is the overall information that we can deduce from this given question. So you can see based on this, the answer will be option A. I hope you understood. So that's enough for this lecture. In the next lecture, we will continue our discussion. We will continue the discussion of synthesized attribute, inherited attribute. We will see S attributed SDD, L attributed SDD, evaluation of SDD. These concepts we will see in the next lecture. Okay. Thank you, everyone. I hope you understood everything that we have seen in this lecture. Okay. Thank you.